Good afternoon and welcome to this video for the level 3 acids and bases for level 3 aqueous systems. So we're just going to get straight into it with some revision from level 2. So we're going to look at strong acids and bases. So strong acids and bases such as for example HCl, HBr and strong base which is NaOH, they are able to dissociate completely in water to form its ions. So this is a full reaction, so all of the HCl, for example, all of the HCl acid particles are going to dissociate to form hydronium and Cl- ions. So we will express this in a reaction by using a direct arrow to indicate the reaction goes to completion. So there are no more acid or base particles remaining after the dissociation. So for this example, we have HCl and H2O. So after the dissociation, there is only Cl- and hydronium ions in the solution. So the electrical conductivity of a solution depends on the relative concentration of the free moving ions in the solution. Because all strong acids and bases will fully dissociate in water to form its ions, which ions are free moving in the water, therefore all of these strong acids and bases will have a good electrical conductivity. To calculate the pH of a strong acid or a strong base, the hydronium concentration is equal to the concentration of the acid if it's a 1-to-1 stoichiochemical ratio. So in this case, if we have HCl and H2O, we know that 1 mole of HCl is going to dissociate to form 1 mole of Cl- and 1 mole of hydronium ions. So therefore, the concentration of the acid is equal to the concentration of hydronium. And then you can use the pH equals to negative log of hydronium concentration in order to find out the pH, okay? And for strong bases, you can use a similar idea to calculate the concentration of OH- ions in the solution, because 1 mole of, for example, if we have NaOH, 1 mole of NaOH is going to form 1 mole of OH- ions and Na plus ions. Therefore, we can use we can find our OH- concentration, find our pOH, and then we can use that to find our pH. Right, so if we just do a couple examples, so we say we can calculate the pH of a 0.2 mole per liter HCl solution. So give yourself a couple of minutes to try this question. Alright, so in this case, we know that HCl is going to dissociate to give us 1 mole of Cl- and 1 mole of hydronium ions. So in this case, the hydronium ion concentration is also 0.2 moles per liter. So we can use that pH equals to negative log of the hydronium concentration, and that's going to give us a pH of 0.7. Alright, question number 2, we can calculate the pH of 0.1 mole per liter NaOH solution. So in this case, we can use a similar idea to calculate the OH- concentration in the solution. So we know that our OH- concentration in the solution is equal to the concentration of the base, which is 0.1 moles per liter. So we can use that to find the pOH by taking the negative log of the OH- concentration. That gives us the pOH is 1, and we know that pH plus pOH equals to 14 at standard conditions, which is 25 degrees Celsius. So we know that pH in this case is 14 minus 1, which is 13. So pH is 13 in this case. Alright, so in level 3, we're going to be looking at weak acids and weak bases. Before we were looking at strong acids and strong bases. We should have still learned about weak acids and weak bases, but we did not need to calculate the pH of weak acids and weak bases. So in this year, we'll be able to calculate the pH of the weak acids and weak bases. So weak acids and bases are those that do not fully dissociate in water to form its ions. So that's different to strong acids and strong bases because they can fully dissociate to form its ions. But in this case, these weak acids and bases do not go to completion. The dissociation does not go to completion. Therefore, an equilibrium will be established between the acid, in this case, acid or base, and its ions. So usually for these weak acids and weak bases, at equilibrium, the majority will still be the acid particles rather than its ions, because it's only partially going to dissociate. So if we take an example, if we take ethanoic acid as an example, so ethanoic acid reacts with water to partially dissociate to form the ethanoate ions and hydronium ions. So we use the equilibrium arrows to indicate that the equilibrium is established. So therefore, we have both of the CH3COOH and the ethanoate ions at equilibrium. So from last year, we should have learned how to write the equilibrium expression. So we can use a similar idea to be able to write an equilibrium expression for this equation. So we can say that the some K constant is going to be equal to the hydronium ion concentration multiplied by the ethanoic ion concentration divided by the concentration of ethanoic acid. So in this case, the concentration of water, we can ignore it because the concentration of water is constant in 1 liter of water. So since it's just a constant, we actually don't need to consider it because it's not variable, it's not going to change. So in this case, we name K as a new constant, which we're going to call Ka, and it's supposed to be K subscript A, so K subscript A, and this is known as the acid dissociation constant. So just remember that Ka is known as the acid dissociation constant. Alright, so let's talk a bit more about the acid dissociation constant. So this is the Ka we just found. So the Ka, or the acid dissociation constant, is a measure of how much of the acid will dissociate to form its ions. So the acid dissociation constant is unique for a particular acid, so it only depends on the chemical properties of the acid. So it doesn't matter how much water is in the solution, it doesn't really matter. All that matters is what the chemical properties of the acid is. In this case, those chemical properties are going to stay constant. So largely the Ka is going to stay constant for a particular temperature, okay? So the higher the Ka value, the higher percentage of acid particles will dissociate to form its ions, hence a higher Ka value indicates a stronger acid. So the strength of an acid depends on what proportion of the acid particles are going to dissociate to form the ions. With a higher Ka value, that indicates that more of the acid particles will dissociate to form the ions. Therefore, we're saying that acid with a higher Ka value is indeed a stronger acid. So, therefore, we can say that a lower Ka value will indicate a weaker acid because a lower proportion of the acid particles will dissociate to form its ions. So, by using the Ka value, we can actually use this to find the pH of a weak acid. So, let's find out how we can do that in the next slide. So let's use our previous example with ethanoic acid. So in this case, we wrote our Ka expression, which is the product of the hydronium ion concentration, the ethanoic ion concentration divided by the ethanoic acid concentration. So if we look back at our equation, we had the equation for the dissociation of ethanoic acid. So from this equation, we see that 1 mole of ethanoic acid will react with 1 mole of water to give us 1 mole of ethanoic ions and 1 mole of hydronium ions. So we know that before the acid is added, there's not going to be any ethanoic acids in the water because water will not give you ethanoic ions, so that doesn't make any sense. So we also know that there's no hydronium ions present before the ethanoic acid is added. And then the second part does assume that the auto-dissociation of water produces a negligible amount of hydronium ions, because we know that water will have, at standard temperature, 25 degrees Celsius, a neutral solution of water is going to have 1 times 10 to the power negative 7 mole per liter of hydronium ions. But in this case, we're going to assume that hydronium ion concentration is going to be too small so it's going to be negligible, it's not going to be important for our calculations. So we can basically just assume that both the ethanoic ions concentration and both the hydronium ion concentration will be 0 before the ethanoic acid is added. So let's say we have a certain amount of ethanoic acid. So some of that ethanoic acid is going to dissociate, and we're going to get the same amount of hydronium ions and the same amount of ethanoic ions. Because there's the same amount, and then this amount of ions is going to be in the same volume, therefore we can say that the concentration of both of those ions are also the same. So we can say that both ethanoic and hydronium concentration is the same at equilibrium, and that the new concentration of ethanoic acid will just be its initial concentration minus the concentration that's been dissociated. So if we say that X is the concentration of ethanoic acid that's been dissociated, we can use that into our Ka expression, and that's going to give us that Ka is equal to X squared, because we're going to produce an X amount of concentration of the ethanoic and an X amount of hydronium. And then we know that the new ethanoic acid concentration will just be the old concentration minus the concentration of ethanoic that we've just dissociated. So that would be our Ka expression. So right now we see that there's normally they will give you the concentration of the ethanoic acid in the solution, and they will give you the Ka value. So if you have a good aptitude in maths, you should be able to know that you can solve this equation because you have only one variable. So if you can solve this using a quadratic formula, that is possible. However, in level 3 chemistry, we will not be doing that. We can use a simplified method in order to find the concentration of ethanoic acid that's been dissociated. So as I mentioned before, we can solve a quadratic. However, we know that the weak acid dissociation is very, very small. So X is a very, very small number. And usually your concentration of ethanoic acid is going to be a lot bigger than X, okay? So because that is the case, we can assume that the concentration of ethanoic acid minus the amount that's been lost is still going to be approximately the same as what we had before. So we can just say that minus X, we can just consider that as negligible. So if we consider that as negligible, we can say that Ka is equal to X squared over the initial concentration of the initial concentration of the ethanoic acid, and therefore, if we solve for X, we can say that X is the square root of the ethanoic ion concentration multiplied by the Ka value. So that is the formula we'll be using to calculate the hydronium ion concentration of a weak acid, because we know that X is also equal to the concentration of hydronium in the solution. So by using this formula, we can find the concentration of hydronium in the solution. So let's just do a quick example here. So we can say, calculate the pH. Calculate the pH of a 0.3 mole per liter solution of HF. That's meant to say pH. Apologize for that mistake. So we know that the Ka of HF is 6.6 times 10 to the power negative 4. So you can try pause this video and give it a try. And when you're ready, you can keep watching to find out the answer. Alright, so the first type of things you should be doing in this type of questions is you should always be starting off by writing the equation for the dissociation of the acid. So in this case, we're going to start off with dissociation of HF. So that is just going to be HF reacted with some water, and it's going to exist. It's going to exist in equilibrium with our hydronium ions and our F- ions. So by using this equation, we can therefore write our equilibrium expression using Ka. So Ka equals to the concentration of F- multiplied by the concentration of hydronium divided by the initial concentration of HF. Okay, so at equilibrium, the hydronium concentration is equal to the F- concentration as we used the previous example of ethanoic acid. We know that when initially there's going to be no hydronium and initially there's going to be no of the conjugate base. So therefore, at equilibrium, the concentration of F- is going to be equal to concentration of hydronium. So we can simplify this equation to that Ka is equal to the hydronium ion concentration squared divided by the concentration of HF. So by using our values, we have our Ka and we have our initial concentration of HF. We can find the hydronium concentration. So in this case, we can say that we can just do some math with our calculator, and we should find that the hydronium ion concentration is 0.01407 mole per liter, and we can use that hydronium concentration in order to find our pH, which should have been negative log of hydronium, which is 1.85 in this case. Alright, so that was pH of a weak acid. So now we're going to look at pH of a weak base. So it's a very similar method. So we can find the pH for a weak conjugate base by using a similar strategy. However, this time, instead of saying the constant is Ka, we're going to call this one Kb, standing for the constant for the base. So the strengths, so we should have learned that in level 2 that the strengths of the conjugate base and the acid will depend on each other. So we know that the stronger the acid, the weaker the base will be, and vice versa. So the stronger the base, the weaker the acid. Because Ka and Kb are directly related to the strengths of the acid and base, remember how we said that Ka is a measure of how much of the acid will dissociate. So the higher the Ka, the stronger the acid. So since it is actually a direct measure of how strong the acid is, therefore Ka and Kb can be quantitatively also related. So for example, take for example our previous example with HF. So let's write our equation for the dissociation of HF. It's going to give us hydronium ions and F- ions. Similarly, if we write the dissociation for F- ions, we can also write the Ka first. So Ka equals to F- times hydronium divided by HF. And if we used F- as the base, we're going to get F- reacts with water to give you some HF and some OH- ions. So in this case, since we have a base that's reacting with water, we're going to write our Kb expression. So Kb is equal to the concentration of HF multiplied by the concentration of OH- divided by the concentration of F-. Right, so if you notice that if we multiply these two equations together, so if we multiply Ka and Kb together, you'll notice that since we have Hf on the bottom for Ka and Hf on the top for Kb and vice versa for F minus, they're going to cancel each other out, and all we're going to be left with is Ka times Kb is equal to the hydronium ion concentration multiplied by the hydroxide ion concentration. So you should notice from last year that the product of the hydronium and OH minus is also the ionic product for the water, right? So that is Kw. So we can say that the hydronium concentration multiplied by the OH minus concentration is the ionic product for water, which is at 25 degrees Celsius, that is 1 times 10 to the power negative 14. So therefore, Ka times Kb equals to 1 times 10 to the power negative 14. Therefore, we know that if you have Ka value, you're going to have your Kb value. So they're directly related by Ka times Kb equals to Kw. Alright, so let's take an example of a pH of a weak base. So here is the question, so just pause the video and see if you can try to do this question yourself first. And when you're ready, you can keep watching the video for the solution. Right, so for this question, we are given the Ka of ethanoic acid. So the first things first, we're going to calculate the Kb for CH3CO minus, which is the conjugate base. So using our relationship we found previously, we can find the Kb, which is the base dissociation constant for ethanoid ions. So if we rearrange to find for Kb, we'll find that Kb equals to 5.56 times 10 to the power negative 10. So next thing we can do is we can write the equation for the dissociation. So we can say that CH3COO minus reacts with water to create some ethanoic acid and some OH minus ions. So therefore we can write the equilibrium expression for this equation, which is Kb equals to a concentration of ethanoic acid times the concentration of OH minus divided by the concentration of ethanoid ions. By similar logic as what we were using before for the pH of a weak acid, we know that the concentration of OH minus is going to be equal to the concentration of ethanoic acid at equilibrium. Alright, so we know that, so in this case, the first thing first, you could write that Kb is equal to the concentration of OH minus squared divided by the concentration of ethanoid ions. So now we can use n equals to small n over big M in order to find the number of moles of CH3CO minus in the solution. And by finding the amount, we have the volume of water. We can use that to find the concentration of ethanoid ions in the water. So we can use so we have 4 grams of CH3COONA, so we can use 4 divided by 82 to give us the number of moles of ethanoid ions in the water, which in this case is 0.04878 moles. And we can find the concentration by saying that the amount divided by the volume is going to give us our concentration. So in this case, our concentration comes out to be 0.1220 mole per liter. So now that we have our concentration of CH3CO minus, we can use that to find the concentration of OH minus ions after equilibrium has been established. So OH minus is equal to a square root of Kb times the concentration of ethanoid ions, and that should give us a concentration of 8.23 times 10 to the power of negative 6 moles per liter, and that converts directly to a pH of 8.92. Right, so let's look at pKa and pKb. So pKa and pKb is just values that have been defined because Ka and Kb values are very, very small, and often they're very hard to use. Because it's very difficult to say, oh, the Ka value is 1.8 times 10 to the power negative 5, so that's a really big mouthful. So instead, people have defined pKa values and pKb values, which range from 0 to 14 at 25 degrees. So in this case, we know that pKa equals to negative log of Ka and pKb equals to negative log of Kb. So by taking the negative log of Ka, we're going to get the pKa, and to take the negative log of Kb, we're going to get the pKb. So if we reverse these equations, we'll see that Ka equals to 10 to the power of negative pKa and Kb equals to 10 to the power of negative pKb. So we know that the higher the pKa is, the lower the Ka, and hence because the Ka is lower, then this is a weaker acid. A lower pKa means that the Ka is larger, and therefore this is a stronger acid. Okay, so just remember that pKa is the reverse for the Ka. Okay, so higher pKa means a lower Ka, and a lower pKa means a higher Ka. And a similar logic will apply for the bases. Alright, so let's have a look at buffer solutions. So normally when an acid and base is added together, for example HCl added with NaOH, a neutralization reaction will occur. However, this is not the case with an acid and its conjugate base. Remember, because the acid and the conjugate base will exist with each other at equilibrium, assuming that the acid and base are weak acids and weak bases. So they will both exist with each other at equilibrium. So therefore, a buffer solution is defined when a solution contains both an acid and its conjugate base at equilibrium. So buffer solutions are interesting in the fact they can resist large changes to the pH for small additions of acid or base. So acid would be the hydronium and base would be hydroxide. If acid is added, the excess acid will react with the conjugate base to form the acid will form back to the acid, and this is a neutralization reaction, so it goes to completion. If excess base is added, the base will react with the acid to form the conjugate base. So the added hydroxide and the added hydronium do not go directly to changing the pH of the solution, but instead they're consumed by neutralization of the conjugate acid or the base, depending on which one you add, depending if you add the acid or if you add the base. Like normally if you add an acid to the solution and the acid does not react with anything in the solution, then the hydronium ion concentration is going to increase in the solution, which causes a decrease in the pH. But in this case, your added hydronium will going to react with the conjugate base, and by reacting with the conjugate base, some of that hydronium is going to be consumed in the reaction, and therefore it's not going to go directly into the solution to decrease the pH. Alright, so let's look at an example. So imagine a solution with equal amounts of ethanoic acid and ethanoate ions. If I add hydronium to the solution, we know that the hydronium is an acid and it's going to react with the conjugate base, which is ethanoate, in the solution by neutralization. So in this case, ethanoate reacts with hydronium, and that's going to give us back to the ethanoic acid, which is the acid in this case, and also it's the conjugate acid of the ethanoate as well as water. So the concentration of the base decreases, which is ethanoate, so the concentration of ethanoate increases and the acid concentration increases. Assuming there's no change in the volume, the acid concentration will increase. However, the added hydronium neutralizes the ethanoate ions instead of contributing to the big decrease in the pH. Therefore, we can say that this buffer solution is resisting the big decrease in the pH when I added the acid. So let's look at if I added the base, which is hydroxide. If I add the hydroxide, that's going to react with my ethanoic acid by neutralization, and that's going to create some ethanoate ions and water. So similarly, the concentration of the acid decreases, which is the ethanoic acid, and the concentration of the conjugate base, which is the ethanoate ion, increases. However, the added OH- ions in this case goes towards neutralizing the ethanoic acid instead of contributing to a big increase in the pH. So as you can see here by this example, that the buffer solution is resisting a large change in the pH for small additions of hydroxide or hydronium. Once all of the acid or base is exhausted, so once, for example, if I run out of ethanoic acid and then I add more hydroxide, then that hydroxide is going to contribute to the increase in pH because there's no more ethanoic acid remaining in order to react with my OH- ions. And that's similar logic for hydronium and the conjugate base. Alright, so let's talk about what an effective buffer is. So the most effective buffer occurs when there are equal concentrations of the conjugate acid and the conjugate base. Because when the concentrations are equal in the same volume of liquid, therefore the amount will also be equal. Since N equals CV, the amount of acid and the amount of base is going to be equal. Therefore, the buffer is said to be equally effective in resisting changes for pH for acid and base additions. So if I add either acid or base, they're going to be equally as effective because there's an equal amount of acid that can react with my added base, and there's an equal amount of base that can react with any added acid. So this is the most effective buffer. If the concentration of the acid is greater than the base, then there's going to be less base available in the solution to react with my acid. Therefore, we say that this buffer is less effective at neutralizing added acid because there's less base available to react with my hydronium. Similarly, if the concentration of the base is greater than the acid, then the buffer is less effective at neutralizing the added base because there's less available acid that can be reactive to base. So therefore, it's less effective because less acid can be added. Less base can be added before all of the acid is exhausted. And once all the acid is exhausted, any more base added is going to contribute to a large change in the pH. Alright, so let's talk about the Henderson-Hasselbalch equation. So since the acid and the conjugate base exist at equilibrium, any change to the concentrations of the acid and its conjugate base will also affect the concentration of hydronium. Since that's in the pKa expression, hydronium is in the pKa expression. Therefore, if we change the concentration of the acids and bases, the concentration of hydronium will also change. So different buffer solutions, depending on the ratio of the acid to the base, is also going to have different pHs. So for a general weak acid, we just call it HA. So HA is going to react with water, and that's going to be in equilibrium with its ions, which is hydronium and A- ions. If we write out the Ka expression, it's going to be the concentration of A- times the concentration of hydronium divided by the concentration of the acid. Okay, if we take the negative log on both sides, we say negative log of Ka equals the negative log of the product of the ions. Then we're going to get negative log of Ka equals to negative log of everything on the right hand side. And negative log of Ka, we know that's equal to pKa. And we know, and in logs, we know that the logs can be split up. So basically the sum of the two logs can be put together as a product. So therefore we can also split up the product into two sums. So in this case, we split it up into negative log of hydronium minus the log of A- over HA. So therefore therefore, because the negative log of hydronium, that is also the pH of the solution, we can just write that as pH. So therefore, pKa equals to the pH, and instead of having minus log, we can actually reverse the contents inside the log and then make it a plus on the outside. So we can say that pKa equals to pH plus the log of the concentration of the acid divided by the concentration of the base. So you don't need to understand how this formula is derived, but you do need to understand how we're going to be using this equation to find the concentration of a buffer solution. So what does the Henderson-Hasselbalch equation tell us? So the Henderson-Hasselbalch equation tells us that the pH of a buffer solution depends only on the ratio of the concentration of the conjugate acid and the conjugate base, because the pKa is a constant. So we see here that pKa equals to pH plus log of HA of the acid over the base. pKa is a constant, so therefore pH is only going to depend on the relative ratio of the acid and the base. An observation that can be made is when there's equal concentration of acid or base, so that's when the concentration of HA equals to the concentration of A-, that's going to give us log of 1, and we know that log of 1 is 0, so therefore pKa is equal to pH plus 0, which is the same as pKa equals to pH. So the most effective buffer when there's equal amounts of acid and base, that's going to occur when the pH is equal to the pKa value. We generally say that the solution will constitute as a buffer, which is effective at resisting large changes of the pH for the additions of acid or base, for small additions of acid and base. That is when the buffer is within plus or minus 1 of the pKa. So pH is within plus or minus 1 of the pKa. If the pH is outside of this range, then the acid or base concentration, so either the acid is 10 times greater than the concentration of the base, or the base is more than 10 times greater than the concentration of the acid. And since there's a very, very large difference in the concentration of the acids and the base, this is no longer an effective buffer because the addition of an acid or a base will not be really effective. So basically, if the concentration of the acid is very, very low, it's not going to be very effective at neutralizing the added base. But if the base concentration is very, very low, then similarly, it's not going to be very effective at neutralizing the added acid. So if the pH is within plus or minus 1 of the pKa, we generally say that it's a acceptable buffer. So let's look at an example at using the Henderson-Hasselbalch equation. So we look at a buffer solution of 500 milliliters of ethanoic acid and ethanoate ions. It has an ethanoic acid concentration of 0.250 mol per liter and an ethanoate concentration of 0.1 mol per liter. So question 1 is calculate the pH before any addition of any species. So just calculate the pH as it is right now. Question number 2, calculate the pH after the addition of 50 milliliters of 0.05 mol per liter HCl. So just pause the video and try to give this question a try. Oh, sorry, forgot about the pKa. So pKa of ethanoic acid is 4.74. So please, apologies for that. So pKa of ethanoic acid is 4.74. Alright, so let's have a look at the solution for this question. So the first question is pretty simple. It's just basic use of the equation. It's just a plug and chug as I like to use it. So you have your numbers and you're just going to plug into your calculator and get an answer. So in this case, pKa equals to pH plus log of the acid divided by the base. So in this case, our pKa is 4.74. That's equal to a pH plus the concentration of the acid, which is 0.250 mole per liter, divided by the concentration of the base, which is 0.1 mole per liter. So if we simplify this equation, simplify this by moving the log of 0.5, sorry, if we take the log of 0.250 divided by 0.1, that's going to give us about 0.4. So therefore, the pH is going to be about 4.34 for the solution. Alright, the second part is a bit harder. So in this case, we're going to be adding acid, which is going to react with the base in the solution. So adding hydronium is going to react with the ethanoic ions in the solution. It's always good to write out the equation for the neutralization. So ethanoic ions react with hydronium to get ethanoic acid and water. Alright, so we can find out the initial amount of ethanoic ions by using N equals to CV. We know that the concentration is 0.1 mole per liter and the volume is 500 milliliters, which is 0.5 liters. So the initial amount of ethanoic ions is 0.05 moles. We know that HCl is a strong acid, so it's going to fully dissociate in water to give us our hydronium ion concentration and our Cl minus, okay? So in this case, our amount of the amount of hydronium is going to be equal to the concentration of HCl multiplied by the amount added, which is 50 milliliters or 0.05 liters. So the amount of hydronium added is 2.5 times 10 to the power negative 3 moles. So in this case, 2.5 times 10 to the power negative 3 moles is going to react with 2.5 times 10 to the power negative 3 moles of CH3CO minus in order to give us our ethanoic acid and water. Alright, so in this case, our final amount of ethanoic ions is going to be equal to the initial amount minus the amount reacted, which is 2.5 times 10 to the power negative 3. So the amount of ethanoic ions remaining in the solution is only 0.0475 moles. And we can use that to find the concentration of the ethanoic ions in the solution by using N over V. So now we have 0.0475 moles of ethanoic ions, and the total volume of the solution was 500 milliliters, but then we added another 50 milliliters of hydrochloric acid. So therefore, the total volume of the solution is now 550 milliliters, which is 0.55 liters. So we can find that the concentration of ethanoate is 0.0864 mole per liter. Similarly, because our ethanoic ions is going to react to form more of our ethanoic acid, the ethanoic acid amount is going to increase. So our initial amount of ethanoic acid is just going to be the concentration times the amount, the volume of water, which is volume water. So in this case, we have 0.5 times 0.250. And then we're also getting an additional 2.5 times 10 to the power negative 3 moles from the reaction of 2.5 times 10 to the power negative 3 moles of ethanoic ions and hydronium. So our final concentration of ethanoic acid can be used by finding the amount of ethanoic acid divided by the volume. So in this case, the amount of ethanoic acid is 0.1275 moles, and then we can use that to find the concentration. So the concentration should come out to be 0.2318 mole per liter. And now we have both of the concentrations of the acid and the conjugate base. So now we can plug it into the Henderson Hasselbalch equation in order to get our pH. So 4.74 equals to the pH plus the log of the concentration of the acid divided by the concentration of the base. And if you rearrange, we should find that the pH is equal to 4.31. Alright, so that covers mostly everything about acids and bases in level 3 aqueous systems. I hope you enjoyed this video, and I hope to see you all in the next one. Thank you, bye.